Hello once again, guys. Devan Paddy here. On this video, I'm going to show you how to create a project using MPLAB version 8.92, an older version of MPLAB. Let's get started directly. To create a project, you basically go to project and then you select project wizard. You click next. And then here you have to select for which device you are creating this project for. You can scroll and look for the device and select it, or you can type the device. So I am creating now a project for PIC 16F818. There it appears. I click it and then next. I'm using assembly language to write I'll be using assembly language to write the program. So the tool suite which I'm going to choose is the MPASM assembler. It's already selected by default, so I just click next. And now here I need to browse and create a project file. So it says there, create new project file. I click browse. And then the idea will be to browse to the folder, to browse to the location where you want to create a project, and in that location create a folder. Maybe in some cases it might be on your memory device, but I'm just going to do it on my documents here. So on documents, I'm going to create a new folder and then give it a name, MPLAB project, and then I open that folder. It's either I can double click here or click open. So let me just double click there. I'm in that folder now which I created. See, MPLAB project. Now I need to give the project a name. Let me call it test project and then click save. Now you will see there it will display the location of where your project is going to be created and saved. Full location under documents, MPLAB project, and the name is test project. After that, you click next. There's nothing to add here. For this project, there's nothing to add. We don't want to add files. We don't have any files that we wish to add at this point. So you click next, and then this is just the summary of the project you have created. The device you'll be using is PIC 16F818. The tool suite is microchip MPASM tool suite, and then that's the location of your project file. And then you click finish. Once you do that, you'll see here the test project name will be displayed. This is your test project, and then these are the files associated with your project. Currently, the project doesn't have any files. The basic file you need to create an ASM assembly program for the PIC using this MPLAB 8.92, it's basically the ASM file where you'll be writing your assembly program. The only thing we need is to create an assembly file program. To do that, we can either use a shortcut there that says new file. See this, if I go there, it says new file, or you can go to file and then select it. Either way it will work. So let me just use a shortcut, new file. A new file pops up. This is the file. This is where we're going to write the program. Right. Now we need to save this file and associate it with the project. So you click on this file. It is the highlighted window. And then you go to file, save as, meaning you are saving this file. File, save as, you give it a name. I'll say test.asm. Very important. When you save this file where you'll be writing your assembly program, you need to save it with .asm extension. And then you tick a little box there that says add file to project. And then you click save. What happens? What do you see there? Now, this test.asm appears as a source file under this test project, right? And now this is your test.asm file. This is where you'll be writing your assembly program. Okay, let me just maximize that, and then also probably maximize my font for you to easily see it. Just use 26. All right, let me just write the basic instructions which you need for any assembly program using MPLAB. First, you need to inform the compiler which PIC you are using. Now, on this, before I do that, on this assembly language, there are basic things that you should know. You use a semicolon to denote that whatever you're going to write after a semicolon is a comment. It's not part of the program you are writing. You're just giving definition or explaining what you are doing in the program. Now, another thing is how you structure your program. At the margin, at the beginning, here, at the margin of the page, we leave space for what we call labels. Right, that's where we're going to write our labels. And using tab, I can tab maybe 3 times or 4 times to the right, and then we will have what we call instructions. And then you tap 1 or 2 times. Doesn't really matter how many times you tap. It's just a matter of how you organize or how you want the spacing of your program, but it should be well organized. We have operands, and then if you want to comment line by line, you'll have your label, your instruction, the operand, and then on that line you will then add a comment to say what is that instruction doing. So that's what you will add comment. I will show how these are implemented as we write a simple program. Right. Now, the basic instructions you should always have when you write an assembly program, first is to inform the compiler which PIC are you using. P equals to 16F818. So I'm saying now to the compiler, the PIC which I'll be using for this application or for this program, it's the 16F818. Be aware that that's a P equals to 16F818, not PIC. It's not PIC, it's just P equals 16F818, or whatever the PIC you'll be using in your case. And then the next instruction, also very important, is the include instruction. Include P16F818.inc. You make use of this file. So let me add comments on this. So here, to add a comment, I need to put a semicolon first. Then what comes after the semicolon is regarded as a comment. The compiler is not going to try and execute whatever that comes after that semicolon when you build your program. Now, here, what am I doing? I'm informing the compiler that we are using PIC 16F818. Now here, semicolon, not a colon. This instruction says make use of this file, sort of a library. You can regard this file as a library. Make use of this library. Include this library in your project, in your program. And now I will I'll also explain the significance of that library. So I will say maybe import this file, import or make use of this file. So you are importing the definitions in that file, or the code in that file if it's a code. Whatever is in that file, you're going to make use of it in this program. You are including it in your program. Now, the next thing that you have to do is the reset vector. Origin 0x00. Sorry for that. Origin x0x00. Go to, let's say, initialize. So initialize is a label. Origin OX00. That's what we call our reset vector. Now the reset vector is the program memory location where the PIC will always start executing instructions after any reset. Meaning you power your system on, that's where it's going to start executing instruction at address 00. You reset it via mclear or via watchdog timer or via any other reset, it's always going to start executions at 00 after any reset, right? So we say at reset, go and initialize. So initialize becomes our label. So when you say go to initialize, you need to state where and what is initialized. So this is my initialize. If I say go to initialize, then the program is going to jump to where initialize is. And then at initialize, I will do whatever it is that I need to do. Right. And then you'll write the rest of your program with your initialize there. But now in the end, you need to inform the compiler that this is the end of the program. Right? So it means here you will initialize, and then after initialize, you can write your main program. I haven't done the initialize, I haven't written anything. So this will depend on what is it that you want to do, what is it that you want to achieve, how you want to configure your IOs of the microcontroller and other features of your microcontroller. Right. So, and then the main program will be about what is it that you want to achieve. And if you have to always repeat that, you will have go to main. So whatever it is that you are doing at main, you will forever repeat it. You will always and continuously repeat it doing it. This is the basic structure of how your program should be organized. Now, if I try and build this, select absolute, I shouldn't have any errors. It's built successful. Right. Now, with that said, let's just get into configuration bits first. What are configuration bits? To get an understanding of what configuration bits are, let me just go to configure, and then there's a point, or there's an option there where you can select and set up your configuration bits. So I'm going to select configuration bits and then disable that so that I can modify the configuration bits here. I'm just extending that for you to be able to read and see what those means. All right. Now on default, this is the value for your configuration bits is 3FFF. And then this value will change as you change your configuration bits. For beginners, most importantly, you might write a nice working program, but when you build your circuit or you build your project, it doesn't work because of configuration bits, right? So that's the reason why I want to show you how and what is the significance, the importance of the configuration bit. If you are a beginner, you are most probably not going to use a watchdog type. Disable it. If you don't disable it, your program is going to keep on resetting. It's not going to function properly. And also disable the brownout reset. Disable those two. Most probably you will want to use your RB3 as an IO, not as a low voltage programming. So you go here and then you select RB3 must be a digital IO function. Those are the three major changes you can do, or you should do. Right. The bottom four options, leave them as they are. Nothing to change there. And now, after you have done this, most importantly, note that the RA5, which is your MPLAB pin, pin 4 of your PIC16F818, if you're using the 818. That pin can be used as either an MPLAB pin or an IO pin, right? It can be used as an MPLAB pin or an IO pin. If you leave it as MPLAB, it is fine, but you must pull it high. It must be connected to your VCC through a resistor if necessary, and preferably it must be held high for normal operation. If this pin is floating or it is connected to ground, your circuit will not function properly or will not function at all. So this MPLAB pin, when you leave it, or if you leave it as MPLAB, you need to pull it high through a pull-up resistor. Now let's assume that we are leaving this as an MPLAB and then we connect it to VCC. We pull it high. Now the next thing, okay, the power up time. This you can enable it or disable it. It doesn't really matter at this stage. So let's leave it disabled. Let's look at this. After you have disabled the watchdog timer, you have disabled the brownout reset, and then you have made your RB3 as a digital IO pin. Leave MPLAB as an MPLAB pin, and then you pull it high on your circuit. The only thing that you need to play around with is your oscillator, the source of your oscillator. Now let's look at options and what they mean. You see, you have a number of oscillator options, being the external RC oscillator, which is a clock function on RA6, which gives you a clock function on RA6. The external RC oscillator, where RA6 can function as an IO pin. The internal oscillator with clock out on RA6, the internal oscillator with IO function on both RA6 and RA7. The external clock, and then RA6 is used as an IO there, meaning that external clock goes into RA7, right? If you are using external clock, any of the RC oscillators, pin RA7, pin 16 of your microcontroller will be the one that is used for the IO, the input, the clock input function, and then the other one can be used as a clock out or as an IO pin. RA6 can be used as a clock out or as an IO pin. RA7 will be used as a oscillator input pin if you are using external RC or you are using the external clock as your oscillator option. Now you have high-speed oscillator, you have a crystal oscillator, and you have low-power oscillators. These are the only options, or these are the options you have to choose from, right? Now, if we select, say for an example, XT oscillator, our configuration value becomes 3F29. And now, what does this mean? It means now, on our circuit, we need to make use of a crystal oscillator, and then our configuration value is 3F29. We can either build our project after setting this to update our configuration bits, but the best practice, which I will advise you to do, is to have these settings in the code, meaning you need to use this value in your program so that you don't really have to come back and set up the configuration bit. So to do that in a program, we use the instruction _config, and as a hexadecimal value 3F29 is our configuration settings. Now once we have done this, you save your project, you work on it, you write your code, and then you close your project, and then at a later stage you have to come back and work on it. You don't have to go back to configuration bits. This program will automatically do that. This instruction will automatically set those configuration bits for you. You don't always have to go in there. And then once you know this value and you always want to use this value, you always want to use a crystal oscillator on a PIC 818. When you write a program, you can directly write this with that value without even having to visit configuration bits. We go to configuration bits to set up our configuration and then to get that value. Once we have acquired that value, we no longer have to come back here. We can just use this value in our config instruction. But now this value, it is if we want to use a crystal oscillator. If we change and say let's use maybe an internal oscillator with IO function on both RA6 and RA7. If we choose internal oscillator on both RA6 and RA7, the value changes to 3F38. Right, we can just go into our code and change this. This becomes 3F38, and then we don't have to connect the crystal oscillator on our circuit because we're using the internal according to our configuration bit. Now these configurations, let's come to oscillators. If you open your PIC 16F818 datasheet and then you come to oscillator configuration, all of those 8 options we have on the configuration bits are these ones. These are the options we have: the internal oscillators, the external clock, the crystal, the high speed, the low power. Those are the options we have in the configuration bits. But now let's say for the first case, when you selected the crystal oscillator, what does it mean to your circuit? If you have selected the crystal oscillator, meaning your configuration bit here, it is 3F29. If this is the case, then on your circuit, what does it imply in terms of your physical circuit? This is basically what it means. This is how you should connect on the oscillator 1 and the oscillator 2 pin, which are pin RA6 and RA7 of your microcontroller, the PIC 16F818. This is how you should connect your crystal. You should have this. There's no way that on your configuration you are saying you're using a crystal, and then on your circuit you don't have a crystal connected there. That circuit or that program is not going to work at all. It's not going to run, because the clock, the speed at which it runs, has to come from that crystal oscillator. Right, you need to put it in your circuit. So the values of the capacitors that you put in there can vary depending on the crystal oscillator you are using, the speed of the crystal oscillator, whether it's a 4 megahertz crystal oscillator, 8 megahertz or 16 megahertz, and so on. Right, so the values may slightly differ, but these values are just to calibrate the oscillator. Your crystal oscillator can still work, or your program can still work without those capacitors there. Just connecting the crystal oscillator alone without the capacitor, without that series resistor. Most of the time actually that series resistor is not connected. So if you just have the crystal oscillator connected to pin 16 and 15 of your PIC 16F818, your program should run successfully with your configuration as crystal oscillator. Right, that's what a crystal oscillator means. But now when you choose the internal oscillator, let's say you choose the internal oscillator with IO function on RA6 and RA7, which is an option also available in your MPLAB Well, with internal oscillators, it's actually very easy. With internal oscillators, it's very easy. There's nothing that you need to connect. On your pin A6 and A7, you can read a little bit up on the internal oscillators. There is nothing that you have to connect. You can actually use pin A6 and A7 as IO pins if you're using the internal oscillator. And now the internal oscillator, it's good in terms of maybe when you are building a system that is size constricted, and then also cost is a factor. The fact that you are eliminating one extra component in terms of space and cost, it's going to play an important role. So you can use the internal built-in oscillator of the peak, and then you don't have to buy the crystal oscillator or any other form of an external oscillator. And also you don't have to put it in your circuit, saving space, if that really makes a difference. Now the other option is the RC oscillator, the external RC oscillator. If you have decided to use the external RC oscillator, let's go back to our configuration bits there and then get the value for if we decide to come and say, let's use an external RC oscillator. We have two options there. One with clock out on RA6 and one with IO function on RA6. It doesn't really matter which one you choose. What matters is what is that you're doing with RA6. If you want to use the RC oscillator, the external RC oscillator, and use RA6 as an IO function, then this is the option you will choose. But if you want to use an external RC oscillator and then you want a fraction of that output to come out on RA6, that's what you will select. The clock out on RA6. That's what you will select, right? Let's assume that you want to use the external RC oscillator and then you want to use RA6 as an IO pin, meaning RA7 it's an RC oscillator input pin. RA6 is the only one available to be used as an IO function. When you select that, the value there becomes 3F, 3A. In your program, this is going to be 3F, 3A, and on your circuit, this is what it's going to mean. Either these are the same constructions, right? This is how you will connect your external RC oscillator. You will need an external resistor and an external capacitor. Recommended resistor values is between 3K and 100K, and then the external capacitor should be greater than 20 picofarad. This is a guideline. But now remember, you have to calculate the frequency of this RC oscillator. You will have to calculate, and then this frequency will actually determine how fast your processor is executing instruction. Right. Now, here, what is important for you to know is that you don't just pick any configuration for your microcontroller. The configuration that you choose has to go hand in hand with the type of circuit you have to build. If you choose an RC oscillator, you need to connect the RC oscillator on RA7 pin. If you choose a crystal oscillator, you need to connect crystal oscillator on pin RA6 and RA7 of your microcontroller, and so on. But now if you choose the internal oscillator, then you have a chance, or you have an option to use both those pins, RA6 and RA7, as your extra IO pins. And then you make use of the value you get after setting up your configurations. The value you get there is the one which you use in your config instruction, right? So I think that makes it clear in terms of configuration bits. Now let's look at this include. What is the significance of this instruction? I said this one, it's just to inform the compiler that we are writing the program for the 818. This one is actually saying make use of this file in this project. But what does this file have? Why is this file useful? For an example, let's say you want to configure your port A pins as inputs and port B pins as outputs. So to configure pins, we have to go to bank 0. So I'm going to say bit set file status comma rp0, and now I'm in bank 1 because rp1 on default is already 0. So 00 on rp0 and rp1 takes us to bank 1, or to bank 0. 00 is bank 0, 01 is bank 1. So I've set rp1 to make it 01, taking us to bank 1. Say switch to bank 1. Now that I'm in bank 1, I can access my trace registers. I want to make all port A pins inputs. All of them. So FF, move W to file, trace A. But remember now, in any case, all pins are inputs on default. So here I'm just enforcing them to be inputs. But on default, after any reset, those pins on default will be configured as inputs, and it is at initialize where you will decide whether you still want to keep them as inputs or you want to change them to outputs. And I want port B to be outputs, so I'll say clear file or move 0 into trace B. So the easiest way to move 0 into trace B is just by clearing it, right? Now, let's say for this application, I want to use all pins as digital pins, because on default, most of the port A pins, they have analog feature. So on default, they are analog, so you need to make them digital. Move literal to W, OX06, Y06, and then that value, I need to move it, move W to 5, AD con 1. Now this will actually make all, or actually, yeah, make all pins digital IO pins. That's basically moving 6 into AD con 1. Now here, what am I doing? Make all port A pins inputs. Here, make all port B pins outputs. Right. Now, I'm assuming that you have watched the previous videos and you understood what we did on trace A and trace B, and what it means, or how you configure your IOs using trace A and trace B, or using the trace registers. Now, the AD con 1 register, let me just explain a little bit on AD con 1 register. I need to go to our data sheet under ADC, under analog to digital converter. Before I do that, let's look at our pin diagram. This is our 16F818. You see it as AN0, AN1. These are analog pin 0, analog pin 1, analog pin 2, analog pin 3, analog pin 4. On RA0 up to RA4, meaning your RA0 and up to RA4. If you use them as inputs and you want to use them as digital inputs, you must disable the analogs, because on default they are analogs, right? They are analog inputs on default. If you want to use RA0 to RA4 as inputs, you need, and you want them to be digital inputs, you need to disable that analog feature of those pins. So to do that, let's just go to the ADC version, the ADC analog to digital converter. Now, when we click here, it's going to take us to the ADC. And the register we use to set up our pins as either digital or analog it is the AD-con1 register. So AD-con1 register. Now the 4 lower bits of this register, the 4 lower bits, meaning bit 0 to bit 3, bit 0 to bit 3 of the AD-con1 register. Bit 0 to bit 3 of the AD-con1 register are the ones we use to configure our pins. So this says analog pin 0, which is RA0, analog pin 1, which is RA1, up to RA4. On default, this AD-con1 has zeros, meaning all those pins are analog, right? But we want them to be all digital. We can use some of the pins as analog reference, positive reference, but we don't want to use them as either analog reference or as analog pins. We want to use them as all of them as digital. There are values we can use to decide and say certain pins must be digital and certain pins must be analog. For an example, if we use this value E1110, this value in hexadecimal is E, it means now only RA0 will be an analog input, the rest will be digital inputs or digital IO pins. But now we don't even want AN0 to be an analog. We want it to be digital. We need to look at the value that makes them all digital, this one. And that value because now of that X says this bit doesn't really matter. It can be made 0 or 1. So if I decide to make it 0, the value is 0, 1, 1, 0. That value is 6. So if the lower nibble, the lower 4 bits of the AD-con1 register make a value of 6, if I make X0, that's going to be 6, or a value of 7 by making that X1. If we move 6 or 7 to AD-con1 on the lower bits, that will configure all the analog pins as digital. All the analog capable pins will be configured as digital. Right? So that's what we want to do. Now, because we are disabling the analogs, we don't really care whether our ADC results are right justified or left justified. We can leave them or we can make them zeros, less justified or 1. It doesn't really matter. I decide to make it 0. And now even the clock divide doesn't really matter because we are not going to use ADC. So disable that. So 0, 0, bit 5 and 4 are on default 0, meaning the 4 upper bits are 0, 0, 0, 0. That makes in hexadecimal a 0. And now this one makes in hexadecimal either a 6 or a 7. So moving 0, 6 or 0, 7 in hexadecimal to AD-con1 will configure your port A pins as digital pins. So that's what is happening here when we move 6 into AD-con1. This will be the same even if I moved 7 into AD-con1. Even if I said move 0, 7 into AD-con1, it will have the same effect, right? Now, after doing that, let's assume now I've configured my input and output pins. I want to go back to bank 0. Bit clear file, status, comma, RP0. Here I'm switching back to bank 0. Switch to bank 0. Now, after I've configured my OO pins, I'm making my own function. I want to read port A because port A are all digital pins. Move file, port A, save it into W, and whatever you read from port A, move it to port B. So basically we are reading port A and writing the value to port B continuously. Read port A, save it into W, write the value on port B, repeat the process endlessly. That's basically our program. Let me build it. Successful. Right. Now, what I wanted us to discuss is this. But for me to be able to do that, I had to write some code there. Now, what does this file, what is the significance of this file? Why do we have to include this file in our program? Let's discuss that quickly. I believe I did discuss this in one of the videos, but it seems appropriate for me to do that now as well. Let's look at, okay, let me start by maybe doing this. Let's look at the data sheet and go back to memory organization. I want us to look at our special function registers. We have special function registers. Now we have these special function registers, they are found in different banks. So for this microcontroller, we have bank 0, which is this block, bank 0, bank 1, which is this block, bank 2, and bank 3. And now, for now, the special function registers we have used are the trace registers, which are in bank 1, and the port registers, which are in bank 0, right? Status registers is found in all the banks. Status register is found in all the banks, most importantly because we are using this register to switch between the banks. So we need to be able to access it in whichever bank we are in, right? We need to always be able to access the status register. Now, these are the names of the registers. Status register is a register at address file address 3. Port A is a register at file address 5. So basically we have registers and addresses of those registers, and then those registers are given names to make it easy. Instead of addressing the register by its file address, we address it by its name, right? Now the reason, or we can actually address it by its file address, or access the register by using its file address, and we successfully write a program. But that will require us to memorize the addresses. Memorizing addresses is not as easy as memorizing and knowing the names, right? So let's go back to the program and see. I want to declare something. Let's say I say trace A is a register at address, okay, let's look at trace A. Trace A is a register at address 85 in hexadecimal. 85 in hexadecimal, okay. So I'll say either 0x in front, or I can just use hex 85. And now let me build my program. No errors, right? But what if I say trace A is a register at 87, for instance, and I try to build this? You see, I get an error there, and then the error it says trace A duplicate label. It means now I'm redefining trace A, and I'm defining it twice as two different things, which can be. You cannot have two labels, the same thing defined twice at different, or as different entities. It's not going to work. It means now it says I'm redefining trace A as 87. But now if it says I am redefining trace A, see, if I double click on this line, it's going to take me here to trace A as 87. That's where the error is. It says the duplicate label. But when I have trace A as 85, it doesn't give that error. Right. Now, let's leave it this as 87. It gives an error because it says I'm redefining trace A. Let me take this redefinition and put it at the top, or just before the include instruction. Let me put it before the include instruction and build this. Still giving the same problem. But now, according to this is the program. The program starts here, it goes down. I am first defining trace A as 87, and then it is also defined again somewhere. So when I double click here, it's going to take me to the redefinition. And when I double click there, you see this is trace A. It opened the file, and then trace A has been equated to 85. And then where does this come from? Because I didn't write such a big program. I have just a small program. What is this? Where does it come from? If you look very carefully, you will see that this file is basically your p16f818.inc file. That's the file you are making use of in your program. That's the file you are including in your program. So the include file, the .inc file, which you are including in your project, has all the names and definitions of special function registers and their bits. Trace A is 85, trace B is 86. So these are all registers in bank 1 is going to define them. All registers in bank 2 is going to define them. All registers in bank 3, and so on. All registers in bank 0 is going to define them and give them the addresses according to the table, according to this. Status being address 3, FSR being address 4, port A being address 5, port B being address 6. So that's basically what it's going to do. Status is address 3, FSR address 4, port A address 5, port B address 6, and so on. The same applies in bank 1 and bank 2. And it further goes and says status register has 8 bits. What are the names of those bits? RP0 is the name for bit 5. RP1 is the name for bit 6 of the status register. And then the same applies to port A. You have RA0, RA1 up to RA7. Port B, RB0 up to RB7. The incon register and all the other registers, the special function registers in your microcontroller. So the include file specifies the addresses of the special function registers, right, for you, so that you don't have to do the include instruction. We don't have to do the equate. We don't have to do this. Because let's say I get rid of this, and then I decide that in my program I'm not going to use the include instruction, and I try to build this program. So I'm commenting it out. It's not part of the program anymore. I try to build. You see how many errors I have now. Symbol not previously defined. The compiler says, I don't know what status is. I don't know what RP0 is. I don't know what trace A is. Because if you are not making use of the 16f818.inc file, then it means you are not defining the names of those registers. You cannot use those names. You cannot use them because you first need to define them. And that include P16f818 does that definition job for you, so that you don't have to define what status is, what trace A is, what trace B is. Right. That's the purpose of this file, and then that's the reason why we are including it in our program, so that it defines all the names of special function registers, so that we can use the names instead of using their addresses, or instead of defining them ourselves in the program. Right. For now, I think that concludes today's video. I'll post more videos trying to actually make it easy for you to follow through and understand peak assembly programming. All right, now thank you guys. See you on the next video.